Okay, so I have my second favorite Steffi here. Okay, this is my neuron Steffi. You got it that way? Okay. So, in thinking about neurons and parts of neurons and that sort of stuff, one of the things that we're going to learn about when we get to the spinal cord section of the course is the number of neurons it takes to go from, say, my finger. How many neurons does it take if I have my finger touching a Steffi? How many neurons in sequence does it require for that sensation of touch to reach my parietal cortex? I hear a lot. Okay. Any other thoughts? There is an answer.
1,000.
Sorry?
100,000.
No, not 100,000. Believe it or not. Lower. Not 1.
10.
No.
2.
3. There's just 3. Okay, and believe it or not, so imagine that there's a neuron. Well, so if you want to use my finger example, so I can feel this touch. There's a neuron that's involved in that touch, and that relays the information to my spinal cord. Okay, depending on which pathway is being used, it can either completely ascend and synapse in the medulla, or it can synapse immediately into the spinal cord. So if you have a person with a really long neuron, that's a really long neuron, right? So you have your cell body, and then your axon does the rest. And then from there you go into the thalamus, and then from the thalamus you go to your somatosensory cortex. So 3 neurons in sequence. And thinking about motor function, how many neurons in sequence does it take for motor function to come from my central gyrus to movement of my hand? How many neurons do you think in sequence? 2. Just 2. Okay? So there's neuronal cell body is in the motor cortex, and that comes down, crosses over at the level of the medulla, comes down to your spinal cord, and hits your lower motor neuron that's sitting in the ventral great horn in your spinal cord. And from there, that neuron goes out and innervates the muscle. Okay? So just basic information for you. Looking at parts of a neuron, I'm going to put him away and then move on to this. Talk about some basic parts of a neuron. Does anyone know what these are called? Okay. It's parts of a neuron. And this is going to be the part of the neuron that receives sensory information. Yeah, these are your dendrites. Dendrites. Okay. And another part. Something like this. So then these are all dendrites around the outside. And then there's another part of the neuron that I'm going to put in here. And this is the part of the neuron that contains the nucleus, which is there, the cell, and mitochondria, and all that other good stuff. Does anybody know what part of the neuron this is? Yes, it's a cell body. It's a cell body or a soma. Okay, same word. Okay, so this is going to be your neuronal cell body. Okay, neuronal cell body is also known as, AKA, soma, S-O-M-A. Okay, dendrites receive information. The neuronal cell body has all the basic parts of a cell. And then moving on down, very specific to a neuron, there's this part. It's kind of like a connector neck, if you will, between the neuronal cell body and the next part. Does anyone know what that's called? That's called the axon hillock. So right here, so this is just a connector. Axonhillock. Okay, axon hillock.
It's just the top portion.
So it's like this purple area right here, and I think of it as like a neck connector. So if this is the head, this is the neck connecting down to the next part of the neuron. It has a special function. I'll talk about the importance of the axon hillock in communicating reaching threshold for an action potential. Okay, moving on down. We have this long portion. Does anybody know what this is called? That's your axon. Yep. Yeah, so the axon hillock simply connects the soma with the axon proper. Okay, and the last part is going to be down here. Anybody know what this part is called? Your synapse is going to be in here. Okay, that's going to be your presynaptic axon terminal. That doesn't work. That's there. Okay, so I'm thinking about this is going to be, let me write it down. Okay, this is your presynaptic axon terminal. There's the axon terminal. I'm calling it presynaptic. That means it's on this side of the synapse between these two axons, between these two neurons. So in thinking about this, so if the dendrites are receiving information, that information is traveling through the axon hillock, down the axon to the presynaptic axon terminal. That means the flow of information is going in this direction. So this way. That's your flow of information down the neuron. Okay, so that information is communicated through to the dendrites. Comes down the axon to the presynaptic axon terminal. And it's going to communicate information to the next neuron in sequence. And then in between this axon terminal and these dendrites, there's a space. I'm just going to shade this space here. Does anybody know what the space is called? Yeah, that's your synaptic cleft. Great. It's your synaptic cleft. Okay, so you go from your presynaptic axon terminal, your synaptic cleft. And we've already labeled this as a dendrite, but in this particular case, it's going to be your postsynaptic dendrite. So any of these will be the same. Postsynaptic, or behind the cleft. It's your postsynaptic dendrite. This is is just a great big overview of the whole thing, and we're gonna kind of look at it again another way. But overall, we have basic parts of a neuron. One basic part is going to be your dendrites, responsible for receiving information. Then your neuronal cell body, or your soma, houses all the basic machinery of the cell. Your axon hillock, kind of like the neck between the body and the axon. And then your presynaptic axon terminal. There's a space between adjacent axons, or neurons, and that space is known as your synaptic cleft. And there's also your dendrite here. This happens to be a postsynaptic dendrite because it's after the synaptic cleft. Questions? That make sense? Thinking about information flowing down from this neuron to this neuron. So thinking about if I had to touch my stuffy, that information would go in this direction to the next neuron in sequence. Yes? Yeah.
Just like there's a signal. Is signal disrupted if like the rails are messed up?
So the axons can work, not necessarily dendrites as much as axons. Okay, axons can be cut. You can think about a nerve injury, right? You think that you cut the nerve. Other things we're going to talk about at the end of this talk are going to be myelination or disruption of myelination for the axon. So we'll definitely get to that. And there are lots of different things that are important in the process of neuronal communication. And there's extra dendrites hanging around, so if you lose one, not so much. It's not as important as cutting that axon. Okay. Other questions? Makes sense? Okay, great big overview, just how things are working. Okay, let's move on in action potential. Have you guys done action potential yet in physiology? You have physiology right now. Have you done it? Since you're nodding a little bit? Okay. So if I put this up here, it's going to look a little bit familiar to you. Something like that. If you had to draw action potential. Dr. Blair goes into a whole lot more detail about action potential than I do. I just need to teach you what you need to know to be a PT. Okay, and that's as much. You need to understand the basics of what an action potential looks like and what it is. So if I had to start out with my action potential, I'm going to be here. Okay, I'm going to start out at minus 70. Does anybody know what minus 70 millivolts represents? Resting membrane potential. Perfect. Okay, so we'll start out here. And we'll say, I'm going to label that number 1. Okay, so on the y-axis, you have your membrane potential in millivolts. We're starting out at minus 70. The x-axis is just a linear sequence of time. Okay, and I'm going to label number 1 over here. And that's simply my resting membrane potential. Okay, and that's minus 70. Okay. The first thing that has to happen if I'm thinking about touching my stuffy, okay, I have to be able to feel the touch. Okay, in order for me to feel the touch, that's going to be a graded membrane potential, not an action potential yet. So it's a gated mechanism. Okay, so if I don't quite feel, I'm touching, but I don't quite feel it yet. Okay, so nothing's really happened. And that graded potential would be represented by just a little bit here, like that. So I almost felt it, but not quite. It's not quite enough to get me to reach minus 50. And I'm going to get my action potential. Okay, and this is going to be called local potential. Okay, and that represents that I haven't quite reached my threshold. Okay, it wasn't a strong enough signal to get me there. Okay, and this is mechanically gated. Okay, mechanically gated means that something has to trigger the mechanism, whether it's going to be touch, whether it's going to be pain, whether it's going to be proprioception. My body has to do something. It's a mechanically gated potential. Okay, not quite, it has to be strong enough to reach threshold, which is going to be minus 50. If it's not quite strong enough, then I don't proceed from the local potential or the graded potential into an action potential. Does that sound familiar? Have you heard that before? Yes? Okay, good. All right, now, didn't quite reach it, but then the next time I try and touch this stuffy, I felt something. Okay, so now I'm going to go up. Okay, once I hit, what is minus 50 here? I'll go ahead and do that. Let's label minus 50. If I had to label minus 50 as something, what would that be? Yep, that's my threshold. Okay, minus 50 millivolts is going to be my threshold. And at threshold, what happens is that, not mechanically gated, these are the voltage gated sodium channels. Open. Okay, those voltage gated sodium channels open. So that means here I have sodium coming into the cell. Okay, as sodium is flooding into the cell, the membrane potential is going to become much more positive. Okay, until I reach a point up here, point number 4. Point number 4, my sodium channels close and my potassium channels open. So here sodium is coming into the cell, and at point 4, sodium channels close, so sodium stops coming into the cell. What happens is potassium starts leaving the cell. That's what this represents. Bless you. Okay. Graded potential has to reach threshold, or the local potential has to reach threshold. Once that happens, then it's an all or none phenomenon. As soon as you reach threshold, you're just going to go. That's an action potential. Sodium channels are going to open. Sodium's going to flood into the cell, make the cell super positive. Okay, it's a voltage gated channel. And at one point, sodium channels are going to close, potassium channels are going to open, and that potassium is going to leave the cell, making the cell much more negative. Comes down to a point where it hyperpolarizes a little bit because the potassium is still leaking out, and then it comes back, and it just comes back to resting membrane potential. That's it in a nutshell. That's an action potential in a nutshell. Hopefully that's a review, and I'm sure Dr. Blair will get into a whole lot more detail, but this is what you need to know for the purpose of neuroscience. Any questions about that? Pretty straightforward. Okay, so the difference between a graded local potential and an action potential. Action potential is going to be your voltage-gated sodium channels, your mechanically gated channels, just getting enough sodium in to bring the cell up to -50, which is threshold. Okay. All right, let's move on to synaptic communication. Okay, back to the basic parts. Have a label. And kind of thinking about this, I'm going to take the first part with all the basic labels and then add in the action potential and then show what happens at the end to have this neuron communicate in sequence with this neuron. Okay. So these, again, what part was this? Dendrite, yep. Okay, start with your dendrite. Your dendrite is going to be that local gated potential, mechanically gated potential. Okay, the mechanically going down,